All right, so what we've done is we've shown how sigma 0 and sigma 1 are both closed under union, intersection, I wrote intersection and then union, concatenation, function composition, and star. They're all composed, and they're all closed under these things. We've also talked about how we can turn an individual DFA into a Turing machine. So we showed that DFA is inside of Turing machine. That's not really the right way to say this. What we really want to say is that the regular languages, they are inside of sigma 0, because what we can do is we can say, given a DFA which has Q sigma Q0 delta, which goes Q cross sigma arrow Q F, which is a subset of Q, we can turn that into Q prime sigma gamma Q0 prime delta, which goes Q cross gamma arrow Q cross gamma cross LR, and then QA and QR. How do we do this? Q prime is equal to Q unioned QA and QR. Okay, so we just add two more states for accepting and rejecting. Q0 prime is just going to be Q0. Gamma is just going to be sigma with blank added. All right, and then what are we going to write for the delta function? So delta prime is going to look like this. Qi of C is going to equal Qj blank. Actually, we don't even need to write Q blank. So it's going to equal, we're going to call the original delta function on Qi and C, and we're going to write a blank and move right. Okay, and then what we're going to do is we're going to say that delta prime of Qi and then a blank, which we'll only see when the thing is done, is going to equal Qa blank right if Qi is inside of F, and it's going to equal Qr blank R otherwise. Okay? So what this shows us is that every single individual regular language is inside of sigma 0, meaning that it's decidable. But what we're going to do today is we're going to have a much, much more powerful theorem, a much, much more interesting theorem. What we want to do is we want to say that there is a category, there is a problem, and we're going to call this problem a DFA. All right, now what strings are inside of a DFA? The strings that are inside of a DFA, we're going to say that W is inside of a DFA if and only if W equals, and now we're going to do some magic, the encoding of the pair MX. Okay, and I'll describe what this is, where M is a DFA and X is inside of the language of that DFA. All right, now what does this mean, the encoding of this pair? So remember, a DFA is some Q sigma Q0 delta and F. Well, Q, you can really think of Q as just like a number. Even though we normally write them down with labels, you could really just say, well, all Q is how many states are there? How many states? So let's suppose that there are 4 states. Well, Q0 is just which of those? So maybe we'll say that it's state 2 is the start state. Okay, and what's F? Well, F is the length of Q bits. It basically says, here are the ones that are inside of it. So for instance, maybe there are, actually, you know what I should do? I should write an example. So suppose that we want to talk about this DFA. where we loop on a 0, on a 1 we go here, we loop on a 1, we go there, on a 0, and this is the accepting state. Okay? So what we'll do is we'll say that there are two states, and which of these is the start one? Well, it's the first one, and which of them are accepting? The first one's accepting. So this is a bit mask, okay, and that's the first one. Now what's delta? Well, delta, recall, is just Q cross sigma arrow Q. What that means, what it is it's a little table that says if you're in state 0 versus in state 1, and if you see a 0 versus you see a 1, where do you go? Well, if you're in 0 and you see a 0, you go to 0. If you're in 0 and you see a 1, you go to 1. If you're in 1 and you see a 0, you go to 0. And if you're in 1 and you see a 1, then you go to 1. So what we could do is we could encode this as a binary string like the following. We could write first how many there are, and we'll do this as a unary encoding. A unary encoding has 0, 0, 1. So the number of zeros is how many things that there are, and then the 1 says that we're done. Okay? So there's 2 of them. Then now that we know how many there are, we know how many bits it will take to encode a single index. So now we have to say which one of these is the start state, and so we'll say that that is 0, the first one. And then we don't need to have any sort of padding for storing the next thing, because we know how many bits it will take to store a single index. Basically, this determines the bit length of all the other numbers that we're going to encode. So we got 0, 1, 0, 0, 1, and then we get 0 for Q0, and then we have to write delta. Well, delta is just this table right here, so we'll just write it out. We'll write 0, 1, 0, 1. So we have 1 bit for this entry, 1 bit for that entry, 1 bit for this entry, 1 bit for that entry. Then the next thing that we need to do is the bit mask for F, so we'll just write 1, 0. So that means that this table, this number right here, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, that describes this machine right here. Okay. Now, what we could then do is say, well, we know exactly how long this is going to be. And so once we have exactly that many bits, all the bits that get left over, all the bits after this, they are just the input to this machine. So let's suppose that the input would be 0, 1, 1, 0. So in that case, that means that 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0 is inside of a DFA. Because what a DFA is it is the language of strings that are encodings of machines and encodings of inputs, where those inputs are actually inside of the language of the DFA. Now we can do this for any DFA. Any DFA. Like we could make a more complicated one. Do I want to bother writing a more complicated one? All right, I'll just do one more example. And I'm just going to do like a random thing. So we'll have 4 states. Here are the 4 states. And we'll say that this is the start state. And we'll say that on a 0 you go there, on a 1 you go there. You're going to loop on a 0 here, on a 1 you're going to go there. Ooh, no, that's not good. Oh yeah, here we'll go there on a 1, and we'll go back here on a 0. And in this case, we'll go there on a 0, and we'll loop on a 1. I have no idea what this language means. Okay, so how can we encode this? Well, first of all, there's 4 states. So we're going to have 0, 0, 0, 0, 1. Okay, so that's how many states that there are. Then the start one is 0. All right. Then what we need, so this is Q. This is Q0. All right. Let's put F next. I think that's nicer. So then we get, let's say that this is 0, this is 1, this is 2, and this is 3. So that means that our F is 0, 0, 1, 0, and so that's F. Then we need to do delta. Okay, so what's delta? Well, delta has 0, 1, 2, 3, 0, 1. Okay, so what is the table? Well, if you're in 0 and you see a 0, you go to 1. If you're in 0 and you see a 1, you go to 2. If you're in 1 and see a 0, you go to 1. If you're in 1 and see a 1, you go to 2. If you're in 2 and see a 0, you go to 0. If you're in 2 and see a 1, then you go to 3. If you're in 3 and see a 0, then you go to 1. And if you're in 3 and see a 1, then you go to 3. Okay, so we got to write this out. So the first number is 1. So we write 0, 1. Then there's 2, which is 1, 0. Then there's 1, which is 0, 1. Then there's 2, which is 1, 0. Then there's 0, which is 0, 0. Then there's 3, which is 1, 1. Then there's 1, which is 0, 1. And then there's 3, which is 1, 1. That is the delta function. Okay, so this right here is the encoding of this machine. Then we could write an example string. And so the example string would be something like, you start and we'll go 0, 0, 1, 0, 1, 1, 1, 0, 1. So that string right there is accepted by this machine. Okay? So this string right here, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1 is inside of a DFA. Okay? So how could we make this machine right here, this ADFA machine? It's a machine that you send it in, and it will determine if the DFA that you gave it accepts the given input. Essentially, this thing that I showed right here, where we can take a DFA and convert it into a Turing machine, is like a compiler. It's like a compiler that takes as input DFAs and returns Turing machines. In contrast, what a DFA is, so a DFA is an interpreter for DFAs. It is a single Turing machine program that includes as part of it all the behavior of every single DFA. Could we make that? Well, it's kind of easy to imagine how it would work, actually. Basically, what we would do is we could take this as the input. Okay, then we could copy it into two other tapes just for convenience. We'll have one tape which is going to be the current state. Here, let me write this. So tape 0 is going to have the encoded version of M and W. And what we'll do is we'll make it so that tape 1 is going to have the current Q. And then tape 2, let's make it so that it has whatever W is. And then all we do is we make it so that we look at Q, we look at the current Q. Of course, we start off, right, with tape 1 being Q0. You know, we like read the encoded version, we copy whatever Q0 is into that spot. Okay. Then what we do is we look at the first character inside of W, and we say, okay, well, I need to go look up inside of this table what row I'm in by looking at tape 1. Then once I know what row I'm in, then I look at the appropriate character inside of here, and then I just see the number there, and I replace the tape with it, and then I just move right on the W tape. And I keep doing that until the W tape is over, and then I just see if the state that I'm in has a 1 marked inside of F. It's kind of easy to imagine how to implement this, actually. So that means that a DFA is definitely something that is inside of sigma 0. So that means that Turing machines can represent not just every individual DFA, but there's actually one Turing machine that can implement all DFAs, which is really remarkable. So what we could do also is we could write a NFA, where what a NFA would do is that a NFA, it would describe all the NFAs. So it could be implemented as like the backtracking semantics, it could be implemented as the forking semantics, it could be implemented as the, it could also be implemented by taking the NFA, compiling it into a DFA, and then running that with a DFA. We could also write a CFG or a PDA. And what these would do is they would simulate deriving a context-free grammar or running a PDA and whatnot by using all the ideas that we've talked about so far about how to interpret them. In fact, in some ways, these programs right here, they are what your project is. What your project is to build a DFA, but you're doing it in Python or something like that. Okay? Now, what about the problem ATM? The problem ATM, it would mean that MW is inside of ATM if and only if M is a Turing machine and W is inside of the language of that Turing machine. That is an interesting problem. What that problem means is that we would take an encoding not of a DFA, but an encoding of a Turing machine. And obviously, it's very similar, right? You're going to say what the queues are. You're going to say what the start state is. You're not going to say which one of them. I mean, basically, you need to have the index of the one that's accept and the index of the one that's reject. So it's actually simpler than F. And then you have delta, and delta just looks exactly the same, except that rather than the entries being just the index of the next state, you would need the index of the gamma, right? Because you want to say, here's how many queues there are, here's how many gammas there are, here's the start state, and then you just have, indices for everything. So the thing is that Turing machines are kind of big. So okay, so here's what I'm going to do. Did I ever write a really short Turing machine? Here's what we'll do. I don't know if this is possible. I'm going to see if I can copy and paste from another document. So its target is going to be 23.6. All right, so when did I introduce Turing machines? That was one. And 18, was that the first time I talked about Turing machines? Yeah, okay, that was it. So we'll go to 18. And that's definitely a Turing machine. Is that the simplest one I've got? This one's kind of complicated. Yeah, we'll do this one. All right, so let's see. So we'll highlight all this. All right, and we'll say copy. Now, go over to 23, and we'll paste. Oh man, good job, remarkable. Okay. All right, so this Turing machine right here, how could we encode this one? Well, how many states are there? There's 1, 2, 3, 4, 5, 6, 7, 8, plus the reject state, so that means that there's 9. So we're going to encode Q as equal to 0, 0, 0, 0, that's 8, that's 4, 5, 6, 7, 8, 9, and then the 1. Okay? Now we need to say what gamma is. So remember, gamma is things that can appear inside of the output. Sorry, inside of the tape. So the things that can be in the output are 0, 1, blank, and smiley face, and hash. So how many things are so 0, 1, blank, smiley face, and hash. Okay, so that means that there's 1, 2, 3, 4, 5 things. Okay, Q0, we'll say, let's just be really convenient. Let's make it so that Q0 is the first thing. So we'll say that that is index 0, and so we have 9 things. So that means that we need 4 bits. So we have to have 9 in binary. What's 9 in binary? It's 8 and 1. So 1, 2, 4, 8. Okay, so that means we need 1, 0, 0, 1. So I think that's 9. Sorry. We're just going to have the first thing. So we just need to say it's the first one. So 0, 0, 0, 0. Okay, that's Q0. Then QA, let's just make it so QA is the last thing. So that's going to be, let's make it so that that's 8. So 8 would be 1, 0, 0, 0, and reject would be 1, 0, 0, 1. So that's the 9th thing. Okay. So now what we need to do is we need to write delta. And so delta, it's got what we do in the start state. And if we're in the start state and we see a 0 versus a 1 versus a blank versus a hash versus a smiley face. Okay, so those are the different things that we need to write down. Okay? Well, if we're in start and we see a 0, then what we're going to do is we're going to go to blank and R. And we're going to go to this state right here. So let's just call that state 1. So that means that this cell right here, it's going to contain inside of it, it's going to contain the number for that state, which it will be 1. So it will be 0, 0, 0, 1. Then it's going to have the symbol for blank. So we did 0, 1, blank, 0, 1, hash, 0, 1, hash. Let me write it like this. 0, 1, hash, smiley face, blank. Okay? So that means that that thing writing a blank is going to be 1, 2, 3, 4, 5. So we have to write the number 5. So number 5 is a 1 and a 4. So it would be 0, 1, 0, 1. Okay, so that's the blank. And then we got to say right. So let's just say that left is 0, right is 1. So that number right there. So every single one of these cells is going to have 9 bits. It's going to have 9 bits for the index of where we're going, the character we're writing, and what direction we're going in. And obviously we could fill out this whole thing. Okay, so my point is that any Turing machine, no matter what it is, we could write it down in this binary encoding, and then we could send it in to ATM. And how is ATM going to work? It's going to work just like this. It's going to have the encoding. It's going to keep track of what state I'm in, what the tape looks like. It's going to look at what it's going to go see the state, compare it to the delta, just do it like you could do this. You know what I mean? It's a huge thing to do, but it's impossible. But it is possible. In fact, what I recommend that you do is you want to Google example universal Turing machine diagram. There are tons of people that have made actual, real actual implementations of ATM. You can go look at the diagram. This is the diagram for that machine. This is not a theoretical thing that, oh, you could maybe do. This has actually been done over and over and over again. And people, there's sort of like a contest, you might say, about people trying to come up with ever shorter and shorter versions of ATM. All right. So we now know that that Turing machines are very, very big. They can do lots and lots of things. But now here is what we're going to talk about next. Here's the next big idea. We would like to know 7, 8. We want to know, is ATM inside of sigma 0 or is it inside of sigma 1? And I'll tell you the answer and then we'll prove it later. ATM is not inside of sigma 0. And here's kind of the reason why. If it's inside of sigma 0, then that means that if you give it a machine that is itself a recognizer that might run forever, how is it going to know that this machine that you gave it run forever? And how can it stop without looping? That is kind of a big problem. So what this is going to mean is that our picture, all, is going to look like this. We've got fin, okay, and fin has got 0, 1. We've got reg, which has 0 star, 1 star. We've got CFL, and CFL has 0 to the n, 1 to the n. Then we've got sigma 0, and it's got 0 to the n, 1 to the n, 0 to the n. It's got ADFA, okay, some cool stuff. Then we've got sigma 1, and that is where ATM is. okay? And significantly, ATM is not inside of sigma 0. And then what we're also going to prove is we're going to prove that not ATM, the complement of ATM, is outside here in all. Meaning that it's something that you can't do with a Turing machine. So this right here is a roadmap for the rest of the class. So we'll take a tiny break from this stuff next time, and we'll come back.